Okay, so I want to talk about Kellerods and Kelasticas, mostly the contribution of Joe to the theory of Kirchhoff rods and elastica. My own interaction with Joe Keller is through a process of both frustration and admiration. It goes into a number of stages. First, I spend a lot of time thinking about a problem, and I think I'm very smart. Second, I do the literature search, and I find that Joe stole my idea. Third part is that not only stole my idea, but he thought about it 40 years before I even thought about it. The next stage is I realize his solution is very elegant, so what am I doing? And the next stage he says, well, if I thought about the problem and he thought about the problem, maybe I'm in good company after all, even if I don't produce anything. So let me give you an example of his contribution over the last few weeks. I've reread the papers that he wrote on various aspects of filamentary structure, about 18 publications starting from 1951 to 2010. So he started his first publication in 47, so you can see through his entire career he went back and forth and looked at a variety of problems. The first one is on the bowing of violin string, and the last one is the famous one on ponytail motion. I do have a theory about where he got the idea about the ponytail motion, but I can tell you that another time. So his contribution is roughly divided into aspects of wave propagation, like the first paper, analysis of PDE with non-smooth coefficient or jumps. A series of paper on contact problem, and a series of paper about optimal or ideal shapes. So let's go through that. The contact problems are very interesting. It looks at essentially the shape of an elastica, whether it's held at 2 points and brought together, or a circular ring under pressure. And he finds all these solutions, and he goes back and forth and as a series of papers on this type of problem. Now, this problem is very elegant toy model. Is really the first one, I think, to really look at this contact and offer solution for this. I think they were very influential, especially in the applied math community in the UK. I think every single department in the UK has somebody who at some point work on flexible tube. Here is a review about this. This is actually the work of Matthias Heil. Of course, we know the work of Tim Pedley. And a lot of these papers start with a simple toy model, trying to get the understanding of the phenomena of what is the effect of pressure when you try to understand buccal state. Recently, I've started looking at it, and of course, I'd forgotten in the meantime, and somebody pointed to me, oh, but Joe Keller worked on that. Yeah, of course. It was so I look at the problem, very nice problem, where you look at the stability of two rings, and it's a work with Gaetano Napoli and Tom Mullin. We're trying now to get some experiments. Here's the problem. You have two elastic, one inside another, and you're just trying to understand the shape. So that's two elastic in contact with the same type. And what's nice, when I went back to Joe's paper, is that he has very nice asymptotic expanding the elliptic function to try to find this bond. It's again a free boundary problem. Another very nice paper is the one that was mentioned by Ray. It's Ropes in Equilibrium with John Maddox. It's not a very highly cited paper. It's actually an outstanding paper. It's really the first and only one paper that looks into the details. And Villaggio reproduced, in his book on solid mechanics, reproduced almost word for word the paper, cited, but there is a full chapter in the book by Pedro Villaggio, the very big book, that has this chapter. It's also the first time in Joe's work that he looks at Kirchhoff rod models. I mean, really three-dimensional equilibrium of rods. And I think that was, and John can confirm, that it was brought by John from his thesis to Stanford. Now, the other set of problems is about optimal or ideal shape. This is a good story, actually. His first paper is on the strongest column. So what is the strongest column? Well, in the words of Lagrange in 1773, is to find a curve which is, by its revolution around an axis, determines the column of greatest efficiency. Essentially, you try to maximize the buckling load for a given volume. It's a tough problem. Lagrange's result was it was a cylinder, which is wrong. It was another shape was proposed in 1851 by Clausen, and when Clifford Truesdell reviewed his work, He said, well, I'm not sure what's going on. There are different solutions. And Joe, he talked about it to Joe, who solved the problem. And the problem for clamp-clamp solution, clamp-clamp condition, is this cigar shape. That's the optimal one. However, in a subsequent paper in '62 with Tadbash, he looks at the generalization to other boundary conditions. And there, they made a mistake. They got a solution that had a point where there was zero radius. Okay, 2 points actually, one at 1/4 and one at 3/4. And it turns out the problem was much more complicated than they thought initially, because the solution, the function they're trying to optimize is non-smooth. And there was also a problem with a double eigenvalue. So the problem was only really understood in the 80s and the 90s by people like Cox, Overton, and McCarthy, and fully solved. Same problem with the tallest column. So that's the problem of finding the tallest column you can create. What is the shape of the cross-section in order to create the tallest column that wouldn't buckle under its own weight? Very nice problem. Again, it's a problem that goes back to Greenhill in 1883 or something like that. Here again, the problem, for the same reason, is that Joe looks at it as a perturbation problem, where you find a single eigenvalue. However, in that problem, there is also a continuous spectrum. Okay, so the solution that he finds is not this one, but another solution. However, McCarthy showed in 1999, point the problem, solve it completely, that's the solution. So to give you an idea, that's 20 centimeter by 86 meter. That's the tallest column that you can do with that type of material. I think it's lead or something like that. Very nice problem. She also showed, McCarthy, that if you slightly change the problem, the solution by Joe was actually the correct one. So you have to rephrase the problem a little bit to find other conditions. Another problem that's of great interest to me was to try to find the tendril shape. So it's a problem I worked in 1998, first with Michael Tabor and then with Tyler Macmillan for his PhD thesis. And by the time we wrote this paper, I think George Oster pointed out to us that, well, you know, I think Joe Keller worked on it. Yeah, of course. So I went back, at least this one was in a lecture note series edited by George Oster. And the problem is solved there. He has all the right elements. I was glad actually I had solved the problem completely. He didn't go find the exact solution or the full solution. And the problem was again that he didn't have the three-dimensional tool that John Maddox would bring to him for the problem. But all the elements were there, including the reference to Darwin. And this is the shape that we found. Actually, there is really it didn't go very far with the problem, but it showed exactly all the ingredients of the problem. Another interesting problem is the problem of the Möbius band. So that's work you've done with Mahadevan. And that's the solution that they obtained. The problem, trying to find the shape of that band, the problem is the solution they solved was based on Kirchhoff-Roth with circular cross-section or rectangular cross-section. That doesn't apply to strips that have to be inextensible. Another solution was proposed by Starostin and van der Heyden in 2007 based on the work of Wunderlich and Sadowski in the 30s. However, their solution turns out also to be not correct, as pointed out actually in a paper this year. So the problem of finding the shape of a Möbius band for an unstretchable strip is still an open one, interestingly enough, despite all this time. So it's a problem that's been around since almost a century, actually. Still very interesting. Okay, so now I want to talk about a little bit of research that I've done with Thomas Lessing, which has the same flavor. Both about looking at very simple systems and trying to develop methods, general methods based on that. So the problem is to try to find stability methods. Let me give you the general idea. We know that if we have an initial value system, if we look at the dynamics in phase space, for instance, if we have a 1 degree of freedom system in a potential, we can draw the phase space. From the drawing of the phase space, we can infer the stability of different solutions. Now, it's very peculiar, this dynamical system, that just by looking at a picture, drawing a picture, you can actually make a conclusion. It's not analytic, it's purely geometry, right? And more generally, if you have a picture like that, you can give that to students, and they will tell you where this point is stable and so on. So you can make a conclusion based on the geometry, actually the topology of trajectories in phase space. Okay? But what about boundary value problem? I can find boundary value problem extended in space, for instance, rods, where I have a finite solution. And I can also draw, like in this case, I'll show you an example in a second, I can draw a solution, like this green solution. If I look at this green solution, can I say anything about the stability? So the point is to try to find a geometric method in order to assess the stability of a boundary value problem. And I'm just going to do it in one-dimensional system, right, to 2 degrees of freedom. Question is the stability. If I look at this, wouldn't it be nice by looking at this picture to assess the stability? Well, we can, and I'm going to show you in a second. So let me give you a very simple example that we completely solve, which is I take a rod with an intrinsic curvature of a given length, and I attach a weight to it. So it's inch here. You are free to change. And this, I can phrase it as a nice variational problem, exactly like you find in Joe's paper. And the equation is very simple. Actually, it's the equation of the pendulum, except I have natural boundary condition rather than Dirichlet boundary condition in this case. So, for instance, if I fix these 2 parameters, the intrinsic curvature and the mass, at this value, I have T solution. I can draw this solution in phase space. Right? What can I say? But I also have all these solutions. For this value, I have 8 different solutions. How do I get which one is stable, which one is unstable? Basic problem. Okay? So let me state the problem. I can define a functional for Lagrangian in 2 variables, theta, well, depending on theta and its derivative. And I'm going to assume in this simple case that it's a one-dimensional, it's based on a potential. Okay, I can have Dirichlet or natural boundary condition. I can also have combination of them. So the problem is to find a function theta which locally minimizes the energy. Okay, so I can expand in epsilon, and to first order obtain Euler-Lagrange equation. And I can decide, I can find solution to that, and I can decide the stability if to second order the second variation is positive on this solution. Okay, for all variation on this space, which have Neumann boundary condition. So that's the gold standard for stability, is to prove the second variation is positive. Okay. That's actually analytically this is extremely hard to do. I don't know of really any simple example where you can actually solve that directly by direct computation. You can do it numerically, and there's a very nice scheme developed by John and by his former postdoc Rob Manning that does that. Okay, so let me give you the second theorem, which is the most interesting one. The first is about the Dirichlet condition. So if I consider a stationary solution of T's energy functional, and I look at the curve in phase space, so I give you a V, and it satisfies the boundary condition, and I draw this curve. Okay, I have the green curve. Now I'm going to compute something out of this green curve. The number of max crossing minus the number of min crossing. How many times I go on the top minus how many times I go below. So that's 1 and 1, 2, minus 1 is 1. Okay, 2 minus 1. Or the equivalent is in phase space, how many times I cross this blue line minus the time I cross this red line. That defines a number I. The theorem states that if I is bigger than 0, the variation is strictly positive. If I is less than 0, the second variation is not positive. That leaves the case I equals 0. In that case, I can define another index, which is the weighted difference in the slope. I look at the potential here, and I write J as the weighted difference between these two. And if J is negative, it's unstable. And if J is positive, I don't know. That's the last case. It's unsolved. OK, let's see how it works on my example. So remember, the stability, I count the number of max minus the number of min. Okay? Here, for instance, I have 1 max and no min. Stable. Or if I look in phase space, I cross once the blue line, which counts for 1, so it's stable. You can also look at the potential. Imagine you put weight on both sides. If it doesn't move, it's stable. It's another way to think about it. So this solution is stable. I can do the same for the other solution. So here is a solution like that. It's unstable because it only crossed the red line. This one is stable because it crossed 1, 2, 3 times minus 2. Okay, at this time of the day, we can still do that. So that's one, stable. And this one is unstable because it goes 1, 2, 2 minus 2 is 0. So you can decide, but if you look at this point, it has exactly the same slope as this one. So the difference in the weighted slope is 0. I'm in the last case, so it's unstable. I have 2 more cases unstable and 2 more cases unstable. So very, very straightforward. Okay, so you can look at the entire solution in parameter space. The solution that all the dashed line are stable, all the solid line are stable. The solution that we looked at are the 8 solution living here. But you can directly extend that to all the solutions. So you can fully solve the stability of this problem, which is very nice. But the method, of course, works for other systems. So let me conclude quickly. First conclusion is obvious. I wish I was as creative as Joe Keller, of course. Who doesn't? But the main point is that there was really 2 sides with Joe Keller's work, which is both the technical aspect, being able to produce very nice and elegant solution, but also the creativity in identifying interesting problems. And that's something that we don't put enough emphasis, actually, in either recruiting or training. And for me, for that part, Joe Keller has always been a role model. So for this particular problem, the take-home message, if you can draw a solution, you know its stability. Okay? And we've looked at plenty of other aspects of that. And this is Thomas, who's worked on that with me. Thank you very much.
We've got time for a couple of questions for Alain.
Yes.
The tallest, what was it?
The tallest column.
Yeah, and what was the one before that? The strongest.
The strongest column.
Did he ever identify, I mean, is there any kind of real object, or was he simply talking about a model?
So it's very interesting because it's really come from the old problem in architecture. You want to create a building. It's really the old Greek problem. How do you shape your column so that it offers the strongest resistance? So it has a very long history in architecture, even in the Greek classics. So it was quite influential after that paper. I mean, that series is the most cited paper among the one I talked about. And people started looking at a lot of other superlative problems. The tallest, the biggest, the longest, and so on. There are tons of application. And this paper is actually quite also cited in the engineering, the civil engineering, where people actually try to optimize different structure. So it become a classic problem, actually, of optimization. And that's why it's mostly cited. So yes, it's definitely influential for that.
You haven't 3D printed it to test it.
John?
You mentioned that there was an article this year saying that
yeah, it's Elliot Fried and Yao Chen. And they show that the family of solution that Starostin and van der Heyden use can never be flattened into a strip on the plane. So it does. You can flatten it to the plane, but it doesn't make a rectangular strip. Ever, except if you start on the plane. So none of these solutions satisfy the fact that if you look at any lines in the strip, they have to keep the length as you fold it to. Right? So the isometric embedding is not satisfied for this solution. And there is not even a proper formulation that you can just feed in the numerics if you try to enforce that condition. So still an interesting open problem. I'm sure the shape that they got, both Joe and Starostin and van der Heyden, are very close to the real one. But the fact is we don't have the real one, which still makes it a very nice mathematical problem, especially since it's a 100 years old problem.
Well, thank you very much. Thank you.